Hello, so if you remember in the last video we were looking at taking some function, okay, and then differentiating it to find the derivative, okay. So that was one version of the derivative. We also had dy by dx, and we also had y prime, okay. And if you remember, we said, well, if we have some polynomial would look something like this. So for example, this is an example of a polynomial, right? We'd normally write it the other way around. We normally write it 3x squared plus 2x plus 1, but essentially this is an example of a polynomial. We said when we differentiate it, we look at each term individually. And we work off of some rule. What was that rule again? That rule was basically saying, well, each term is going to look something like some number, some coefficient, with an x raised to some power. Okay, so when we differentiate it, then the number, the coefficient comes along for the ride. Okay, the power climbs down and multiplies out the front, and then we reduce that power by 1. Okay, now in this video, I'm going to prove that to you. So in the last video, I showed you lots of examples about why it works, but in this video, I'm going to use the Binomial Theorem. So if you haven't watched the video on Binomial Theorem, I suggest watching that one, and then coming back, and then I'm going to show you why this works. So if you remember from first principles what our formula for our derivative function was, so it's dy by dx was equal to the limit as our h, our distance between our x coordinates approached nothing effectively, and then we looked at our y value, so f of x plus h, the difference in our y values, f of x plus h minus f of x, over the difference in our x values, which was just h. Okay, so remember up here I've said that y is equal to f of x, and I've said that y is equal to ax to the power of n, so I can just simply say, well, f of x then must mean the same as y, so I can just simply replace y with f of x. Remember I was talking about that in the last video, okay? So I've got my f of x, but what about then my f of x plus h? Well, if f of x is equal to that, then f of x plus h must mean that whenever I see an x, I just replace it with an x plus h. So in other words, I've got this. Now, I'm just going to look at this in a little bit more detail. So I'm going to look at x plus h to the power of n. Now, with the binomial theorem, this looks something like, well, something plus another thing raised to some power. That's effectively what I've got going on there. And if you remember, the binomial theorem basically states that I start with my x and I increase the powers. So I increase the powers. So I start with x to the power of n and I decrease the powers. And then the other term, I increase the powers. So my x, I start with x to the power of n and I decrease the powers with each term until I get to 0. Okay. With my h, I start at 0 and I increase the powers with each term. So I've got x to the power of n, h to the power of n. So in the next, h to the power of 0. So in the next term, I'm going to decrease my x power. So x n minus 1, okay, and I'm going to increase my h power, so h to the power of 1, okay. What's my next term going to be? Well, it's going to decrease my x power by 1, so x to the power of n minus 2, and I'm going to increase my h power, so h to the power of 2, okay. Then I'm going to carry on going, okay, until effectively what I'll end up with, I'm just going to jump into sort of few terms before the end. I'm going to end up with x squared, okay, h to the power of n minus 2, okay. Now I'm decreasing my x value, so x to the power of 1, okay, and I'm increasing my h power, so h to the power of n minus 1, okay. And then final term, then I'm going to decrease my x power. I'm going to decrease my x power to x to the power of 0, and I'm going to increase my h power to h to the power of n. Now, what's happening with my coefficients? My coefficients come from the choose function. Again, if you haven't watched a video on a binomial formula, don't worry about this too much, but essentially I just do n choose nothing, so I have n objects and I choose none, and then my next one is going to be taking n objects but then I choose one object, then my next coefficient is going to be n objects but then I choose 2 objects, then I'm going to carry on going right the way through until I jump in at this term here and I'm going to be choosing n minus 2 objects from n, and then I'm going to have n objects and I'm choosing n minus 1, and then I'm going to be choosing n objects and I'm going to be choosing n. Okay, now I can do a little bit of simplification here because n choose nothing is just 1. Okay, how many ways are there of choosing no objects? There's only one way, just choose none, right? So that's still 1. Then I've got x to the power of n, h to the power of 0. Well, h to the power of 0 is just 1, so I've got 1 times x to the power of n times 1. So that's just x to the power of n. Okay, what about my next term? Well, n choose 1. How many ways are there of choosing one object from n objects? There's n of them. Okay, so that's my next coefficient, x to the power of n minus 1, and then I'm just going to write my h to the power of 1 as just h. Okay. My next term then, I've got n choose 2. Well, I don't know what that is unless I know n, okay. Then I've got x to the power of n minus 2, h to the power of 2. I can't really do much with that. Then I jump in, okay, this term here. So I've got n, choose n minus 2. Can't do any simplifications there. X squared, h to the power of n minus 2. Haven't made any simplifications there, unfortunately. Okay, this term, n, choose n minus 1. Well, that's the same as n choosing 1. Okay, so in other words, just n. Okay, then I've got x to the power of 1, which I'm just going to write as x. Then I've got h to the power of n minus 1. Okay, then my final term, I've got n objects and I choose n of them. How many ways are there of doing that? There's only one way. Okay, so it's 1 times x to the power of 0, which is just 1. So it's 1 times 1 times h to the power of n. So I'm just going to write that as h to the power of n. So now I can just say, well, x plus h to the power of n is just equal to everything inside that bracket. And don't forget that I've got to multiply by a. So I've just found what x plus h to the power of n was. I've expanded that out to look something like that, like the binomial theorem. Then I just need to multiply every term by a. So when I multiply through by a, that's what I get. Now it's all the same. Basically, what I've got to do is I've got to take all of that and I've got to sub all that into my formula up here. Okay, so let me just do that. Now, it looks horrible, but trust me, a lot of things cancel. So I've got dy by dx is equal to the limit as h approaches 0, okay, of, well, all of that thing, take away that thing. Right, okay. So all that thing there is my f of x plus h. Then I've got to take away f of x. Remember what my f of x was? It was ax to the power of n. So I've got to take away ax to the power of n, and then I've got to divide through by h. So all of that divided through by h. Okay. Well, what can I cancel off straight away? Well, I've got an ax to the power of n there, and I'm going to take away an ax to the power of n. So you're happy that I can just cancel and then cancel. And then look, whenever I see an h, I can just cancel an h off there. So let me do a cancellation. So there's an h there, so I cancel one off there. I can cancel one h off there. What am I going to be left with there? I'm going to be left with n minus 1 there. I'm going to be left with n minus 3 there, won't I? And then I'll be left with n minus 2 there, and I'm going to be left with n minus 1 there. Okay, so what am I left with after a little bit of tidying up? So that's what I'm left with. But actually, that doesn't look too bad at all, because look, now all I'm left to do is just take the limit as h approaches 0. Remember what the limit as h approaches 0 means again? It basically means h, the distance between the 2 points, is getting infinitesimally small so that it behaves like it's at that value. So if h is approaching 0, it means that it's behaving or starting to behave as if it's acting as if it's at that value. So basically, whenever I see an h, that just automatically goes to 0. So that goes to 0. That goes to 0. All these intermediate terms, they all go to 0 because they'll also have an h in, right? These will all have h's in, so this goes to 0 and this goes to 0. So actually, all of these terms, because I'm multiplying by something which has 0 in, because h goes to 0, they're all going to disappear. And so all I'm going to be left with is this term here. So an x n minus 1. So this is what dy by dx is equal to. So just recap what we've done again. We started by saying that we're going to start with something that looks a little bit like this. So y is equal to some number, x to the power of n. That's what our some term in our polynomial expansion is going to look like. So we've got a polynomial in front of us. Every single term is going to look something like that. Okay, well then when we differentiate each term, our derivative is going to look like this. And this is basically what we've proved. So x n minus 1. So this formula, which I seemingly just pulled out of thin air, I've shown you where it comes from, and I've hopefully given you a little bit more confidence when you're coming to use it.